In this 9th lecture, we continue to see how the fundamental constituents of matter were discovered. In this lecture, we will talk about the discovery of the various types of quarks, which are the constituents of so-called hadrons, so baryons and mesons. So, we will talk about nucleons and other baryons, which are composites of quarks, and so are the mesons, and then we will talk about the 3 families of quarks. So, the point-like particles and nucleons were actually proposed by Gell-Mann and Zweig independently, and they said that these make up nucleons. So, the proton is supposed to consist of a UUD quarks. The neutron is supposed to be a composite of the UDD quark. So, U stands for up quark and D for down quark. The name of quark, of course, was given by Gell-Mann, who had a great interest in languages and so on, various languages. So, he took this from James Joyce's book, I think it's called Ulysses or something. Anyway, he picked up that word, the quark, from there. And so, these quarks make up proton, neutron, but also other baryons like the delta plus, actually it should be delta plus plus. Let me change that. This should be delta plus plus, double plus. It has a charge of 2 plus 2. And then we have the delta plus, you have the delta minus, the delta neutral delta, and so on, and other mesons like the pi plus minus, the pi 0, and so on. And this proposal was made by them in 1964. This quark was a very strange thing that they proposed. It had to have fractional charges. So, 1/3 plus minus 1/3 plus minus 2/3 and so on. They were, of course, supposed to be fermions with spin half. Since no free fractional charges were ever observed in Millikan kind of experiments, in other experiments, in many searches that were carried out, it was concluded that they had to be confined to the hadrons, the baryons and the mesons. This, of course, got support much later when the so-called theory of quantum chromodynamics, QCD, analogous to QED in some ways, but richer in structure. There, the quarks were supposed to be asymptotically free at short distances between quarks, but at large distances, this interaction was supposed to blow up, and so no quark could ever come out of the hadron or meson, of the hadron, okay, either the baryon or the meson. But this happened, of course, much later. So, when they proposed, this was met with a lot of resistance from the physics community. They said this is just a theoretical construct to somehow explain the way you have baryons and mesons and so on, but maybe this is just a mathematical construct. However, experiments done in the late 60s at Stanford, which had this 2-mile long electron accelerator, which could produce electrons from low energies of about 4 GeV to about 20 GeV. They carried out a series of experiments, and especially in the deep inelastic region, which revealed partons. This was due to, the word parton was due to Richard Feynman, but they were then later identified as quarks as being the constituents of nucleons. So, this is the key paper, Coward et al. Physical Letters in 1968. So, I am jumping the gun a bit, but just to show you where these quarks sort of fit in, is that you have the standard model of elementary particles, which came about in the mid 70s after after the electroweak interaction was formally accepted in the particle physics community, and so was QCD, quantum chromodynamics, as the theory for strong interactions. So, the interaction between quarks and gluons, which are the intermediaries between quarks, which carry the strong force. but the gluons have a difference from photons in that they, apart from the fact that they are massless like the photon, but they also interact among themselves. Okay, so this is the picture of the standard model of elementary particles. You have quarks, U, D quark, which make up the proton and the neutron. Then you have the charmed quark and the strange quark, the top and bottom, and we'll come to these quarks and how they were discovered. Then you have the photon, which is the quantum of electromagnetism, electrodynamics, and then you have, this is of course, this came much later, the gluon and the Z and W bosons, which are responsible for the weak interaction. We have already seen the other players, the leptonic sector, which is the electron and its associated neutrino. Then we have seen the muon and its associated neutrino. And then of course, we have the tau, which was discovered much later, much heavier cousin of the electron and the muon. And then it also has an associated neutrino, which is called the tau neutrino. In addition to all of this, due to Mr. Higgs, we now think we understand that the masses of each of these particles comes through the interaction with the Higgs field, and indeed this Higgs boson, which which is the particle associated with that field, it's a scalar particle, and it has a mass of about 125. Sorry, this is again a typo. This should be GeV. GeV by c squared. So 125 GeV by c, and this was discovered in 2012 at the Large Hadron Collider in the early runs of the Large Hadron Collider on PP interactions at lower energies. I think it was about 3 or 4 TeV on 3 or 4 TeV, and they discovered signatures which are consistent with it being the Higgs boson, which were posed by Peter Higgs and also many other scientists, for which I think 3 of them got the Nobel Prize also for that. Okay, so let's come to deep inelastic scattering. So this experiment actually used, as I said, the Stanford 2-mile long 20 GeV linear accelerator for electrons. So this is the length of about 2 miles, and this used the linear accelerator principle, which we have talked about in some earlier lecture. When these scatter off nucleons, then the electrons were analyzed by a magnetic spectrometer. Indeed, there were 3 of them here, and the one which was used was this 8 GeV magnetic spectrometer. So this was the top view of the hall which housed these 3 spectrometers. 1.6 GeV spectrometer, the smallest one, then the 8 GeV, and then there is another spectrometer for the 20 GeV electrons. And so the beam comes in from here, the electron beam comes in from the slack 2-mile long accelerator and goes out through this exit. So some of these things are taken from open literature and also from the Nobel lecture of Kendall. So the 3 scientists who carried out these deep inelastic experiments, which told us that nucleons contain quarks, they got the Nobel Prize in 1990. So anyway, this is the side view of this 8 GeV spectrometer. So this is the incident beam on a target, and then this is focused with quadrupoles, and then there are bending magnets which take it up into a detector, of course, which has a heavy shielding because to shield it from cosmic rays. So this is the so-called elevation view of this spectrometer. Okay, so the deep inelastic experiment carried out by this group, the result of that is shown, one result is shown here, where the cross section, deep inelastic scattering cross section is divided by the so-called Mott cross section as a function of momentum transfer squared is plotted here, and at a certain angle, because of course the inelasticity is different for different energy losses. So that's how you get this plot, but the angle is, the spectrometer is kept at 10 degrees, and so the invariant mass that you can construct is of the order of either 2 GeV, 3 GeV or 3.5 GeV, and these are the plots shown here. So, the full line is this one, 3 GeV one is small dashes, and the large dashes are the 3.5 GeV. So, these roughly behave in this same manner. As compared to the elastic scattering cross section, these are way above. So, the deep inelastic cross section is way above. So, in some ways you might say that this is reminiscent of Rutherford's alpha scattering experiment on nuclei, where there was a large excess at large angle elastic scattering. This is not elastic scattering, but this is inelastic, deep inelastic scattering at large momentum transfer is seen by this in this experiment. So, let me come back to this figure. So, this shows that there are point objects which are moving around in the nucleonic volume. In this case is the proton, electron-proton scattering that was measured. Of course, they also have done electron scattering on deuteron, and then you can subtract the cross sections from the deuteron of the proton component content, and then you can get the neutron scattering as well. But this one is for electron-proton scattering, and you can see that this shows you that there are point objects in the proton that are moving over the nuclear volume, but which lead to this inelastic scattering. So, it is believed that when an electron scatters of a point object, which is in this case the quark, then the quark, since it cannot come out, it so-called quote unquote hadronizes, it produces hadrons, and this takes away energy. So, there is inelasticity in this process, and therefore, the electron comes out with lower energies. So, this is how this was inferred. So, this is a very simplistic way of telling you that there are point objects in the nucleon. So, this is as far as the quark content of a nucleon, which is a particular example of a hadron. This is the evidence for that. But then it turns out that U and D are not the only quarks that are present. You also have so-called strange quarks, and these of course were indeed proposed by Gell-Mann and Zweig to explain the kind of hadrons and the kind of baryons and mesons that were seen at that time in 1964. And so, the strange quark, for instance, is supposed to be present in the phi meson, which is supposed to be a SS bar object. Also in K mesons, both the K plus, K minus and the K0 pair of mesons. In baryons, such as the lambda, this should be lambda by the way. So, again a typo. This is the lambda particle, lambda baryon, which is a combination of U, D and S. So, the S quark decays weakly to the D quark, and if you go back, so the S quark here decays weakly to the D quark, and since it is more massive than the D quark, this energy is released in the form of a electron and a neutrino. And since it decays weakly, of course, this the typical time scales are the weak interaction time scales. So, the lifetimes are large, and so these mesons have lifetimes of the order of 0.1 to 10 nanoseconds. The K meson, the lambda, this is so-called hyperon. It's a baryon. It's a heavier cousin, strange cousin of the nucleon. The phi, of course, since it is a SS bar pair, it can annihilate and it can produce particles. So, this has a much shorter lifetime, and so this decays by electromagnetic basically time scales. Okay, so this is so much about the strange quark. Now, there is another quark which is the charmed quark, which if you remember, it was above the, in this tabulation, was above the strange quark, and this was discovered quite unexpectedly in 1974 by two different groups working in, with one with a working with a proton machine at the AGS, the alternating gradients synchrotron at Brookhaven National Lab, which is on the east coast of the US, and by a group at SLAC, which is on the west coast in Stanford. Whereas the Brookhaven experiment looked at protons colliding with beryllium, producing E plus E minus pairs, and so these were detected in spectrometers meant to detect these electrons or positrons. So it's a dual arm spectrometer, and they looked at the the spectrum of this invariant mass spectrum of, that can be generated from the detected E plus E minus, whereas the SLAC experiment actually looked at E plus E minus in collision mode. So the E plus and E minus collide, and then they produce a debris of hadrons, and muons, and whatnot, and they looked for the annihilation products. Both of them almost simultaneously saw a sharp resonance at 3.1 GeV, which was later assigned to be a CC bar, so a charmed quark and a charmed anti-quark bound state. Now, this resonance was, in fact, as seen by the Brookhaven experiment, was so narrow that it was they just saw the detector resolution. In the case of SLAC, they also measured a very narrow resonance, and the surprise was that you see such a narrow resonance, which is of the order of keV or less in width, at an energy of 3.1 GeV. Okay. So it turns out that again the charmed quark decays weakly, and that's why it has a very long lifetime, relatively long lifetime compared to strong interaction time scales, and therefore a narrow width. These are the two papers that are relevant. Aubert et al., which is the MIT Brookhaven collaboration, led by Sam Ting. So this is the paper published. They called it the J resonance, and similarly the other group from SLAC, which was the SLAC University of California at Berkeley, this collaboration. So these are actually back-to-back papers. You can see that this is a 2-page paper, 1404, and there is another 2 or 3-page paper just next to this one. And so this one is called the discovery of a narrow resonance in E plus E minus annihilation. This group called it the psi resonance. So in fact, this particle, this meson, came to be known as the J psi resonance, J/psi resonance. So let's look at the first, the experiment done at Brookhaven, the MIT Brookhaven collaboration experiment led, as I said, by Sam Ting. So the beam impinged on a target, and then using dipoles, the products were guided into a spectrometer, which was a dual arm spectrometer. So what is shown here is one arm of the spectrometer. There are various detectors in between, which were used to characterize the direction and identification of the particle. The second arm, as I said, is not shown here, but it is also there. So it is on, I think it is up and down, so on. So they found, okay, so this is what is shown here is the E plus E minus time of flight spectrum, and in a certain energy band for the invariant mass of the E plus and E minus, and you can see that this is peaked at the prompt. So these are all the events, and these are the events with a mass between 3 and 3.2 GeV. They also fall in the same time of flight region. This is the final analyzed mass spectrum at 2 spectrometer settings. You can see that the resonance that they called the J resonance, its peak position is invariant. Okay? It's the same peak position even if you change the spectrometer settings by some amount. And you can see the number of events, the total number of events is of the order of 250 or so. And the invariant mass peaks at about 3.1 GeV. The SLAC, University of California at Berkeley collaboration, they, as I said, they were doing this at Stanford using the SPEAR facility. So you produce E plus, and then you in the next time bin you produce positrons, and then you cool them and then bring them together in the SPEAR collider ring. And of course, this can be stored in that ring for some amount of time ranging between hours and several tens of hours, and they could look at these collisions with again spectrometers. So the energy dependence of the cross section with very similar spectrometers, by the way, magnetic spectrometers. I think that is, I don't know whether it's there in the subsequent slide. No, it's not there, but it's similar kind of techniques that use magnetic spectrometers. So the energy dependence of the cross sections for the E plus E minus going to various channels, and this is plotted here in the hadronic states, in E plus E minus final states, and also mu plus mu minus, pi plus pi minus, and k plus k minus. These are summed up and shown here. So these show an energy dependence that indicates strong resonance at 3.105 plus minus 0.003. So you can see that this is the energies of the resonance is known very precisely in these E plus E minus experiments. The electron positron, they are very clean probes of matter, and they are also very precise probes. So you can get the energies right to very accurate values. In fact, this resonance had a width which is smaller than 1.3 MeV. The number from the experiment done at Brookhaven would be about 10 to 20 times larger. Okay. Of course, it would also be similar. It would be a upper bound for the width of this state. So it is consistent with the energy resolution of the spectrometers. Later, of course, an excited state was seen at 3.7 GeV, and so while this was called the J psi resonance, this was called the J prime psi prime, usually known as the psi prime resonance. Sam Ting was the leader of the Brookhaven experiment, and Burton Richter, shown here, who led the SLAC experiment. They shared the 1976 Physics Nobel Prize. So within 2 years of this experiment, which caused great excitement in the particle physics community, they got the Nobel Prize within 2 years of their discovery. Now we come to the so-called bottom quark, which was postulated by Kobayashi and Maskawa in 1973 to explain CP violation in kaon decays. Now this bottom quark was discovered later in 1977 by a group led by Lederman at Fermilab using the 400 GeV proton beam, and they had copper, platinum targets and so on. They were looking at the dimuons, okay, an inclusive spectrum of dimuons. So mu plus, mu minus plus x. You don't care about what happens to x, you don't detect that. But you measure the dimuons in a 2-arm magnetic spectrometer. The mu plus mu minus mass spectrum could be fitted with one peak at a rather broad one at 9.5 GeV, width of about 1 GeV, but it could also be fitted by two peaks, narrower ones, at 9.44 GeV and 10.17 GeV, and these would correspond to, it was believed, BB bar resonances, and this was named the upsilon. And in fact, if this assignment is correct, that there are actually two peaks, not one broad peak, then this would correspond to the upsilon and the upsilon prime resonances corresponding to the BB bar states. This paper is published in 1977. So this is a depiction of the 2-arm magnetic spectrometer that Lederman and colleagues used at Fermilab. This is the as you can see, the distance scale stretches over about 30 meters. This is a huge device, and this could of course also be rotated, but in principle. But this is so these two arms capture the muons. Okay, let me apologize. I made a statement that this could be rotated. I am not very sure whether it is rotated or not, but certainly these two arms could detect mu plus and mu minus. Okay, and as a check, they measured in the lower invariant mass region the dimuon spectrum, and this corresponded to the J psi resonance and the psi prime resonance at the right energy, 3.1 GeV and 3.7 GeV. Okay. So, this shows that this is doing the right thing, and this is the spectrum that they measured, the invariant mass spectrum versus the events, of course, put in this, cast in this form, d squared sigma by dm dy. This is the rapidity at zero rapidity. That means at basically in the center of mass perpendicular to the direction of the incoming particles. So, this is done in some units of 10 to the minus 39 to 10 to the minus 35 square centimeter per GeV per nucleon, and from right from about 5 GeV to about 14 GeV. So, what is shown is that there is a bump here, there is a peak here, and maybe there is evidence of a second peak riding on an exponentially falling background. So, there is also another set of points, which is the hollow points, and this is the mass spectrum that is generated with the same sign muon. That means mu plus or mu minus. Okay. And this does not show this kind of structures. This comes about from mu plus mu minus dimuon pair. If you subtract this exponentially falling background, then you get a spectrum like this, and this is the kind of excess that you see, which corresponds to the BB bar or maybe excited states of the BB bar. The apparatus resolution, the spectrometer resolution of the two combined is of this order, is about let us say of the order of about half a GeV. Okay. Then we come to the heaviest quark of them all, the so called top quark, and this was also discovered at Fermilab, but this time using the so called Tevatron collider, which had a 1 GeV proton colliding with a 1 GeV antiproton. So, the antiprotons were first produced, then they were cooled and stored in a ring and made to collide with protons moving in the opposite direction in that same ring. So, although this experiment was done with the TeV operating at a center of mass energy of 1.8 TeV. Okay, this could go up to that. So, the mode of decay measured in this, so the PP bar collides and it produces a plethora of particles, but what is looked for is a signature of the TT bar pair produced. Okay. So, that would then decay into a W boson, which of course we have not talked about yet, how it was discovered. We will talk about that in the next lecture. So, the pair of W's and associated with each W the B quark, which of course then decays into jets. So, the W going to electron or muon plus neutrino, and then the B which decays into jets. This kind of signature was used in the analysis. So, it is a fairly complicated decay structure, but for its time at least. And so, there were two detectors that were there in the collision zones, the so called CDF detector and the D0 detector, and they found a reconstructed mass which was of the order of 176 GeV by c squared at about 4.8 sigma. So, it is a pretty high significance, and if you remember that a nucleon is about 1 GeV mc squared. So, then this is about the mass of a tungsten nucleus. Okay. So, the D0 also found evidence for the top quark, again using similar techniques, but with a different set of detectors. They found this to be with a slightly poorer precision, 199 plus minus 30 GeV by c squared at 4.6 sigma. So, combined, of course, this if you combine these two independent experiments, that you get a significance which is larger than 5 sigma, which is the accepted norm for making a discovery of any kind in particle physics. So, this tells us that the top quark was discovered in the tevatron, and these are the two references, the key papers published in 1995. So, we come to the summary. We have seen evidence for quarks in protons from deep inelastic scattering, and then we have looked at experiments that provided evidences for the strange quark, the charmed quark, the bottom quark, and the top quark. The U and D, of course, were part of the proton and neutron, and so they were hypothesized to be there anyway. Thank you.